The universe is vast, mysterious, and terrifying. Among all its cosmic wonders, one phenomenon stands out as both fascinating and terrifying: the black hole. For decades, black holes have captured our imagination, often shown in movies as giant cosmic vacuum cleaners, swallowing everything in sight. But the truth is far stranger, more fascinating, and infinitely more terrifying than fiction. Black holes don't suck, they warp space-time itself. And understanding them could reshape how we see the universe and ourselves. To understand black holes, we must first understand how they form. Imagine a star much larger than our sun, a giant, blazing furnace of nuclear fusion. For millions of years, it burns brightly, creating energy that radiates out into the cosmos. But eventually, that star runs out of fuel. Its core can no longer withstand the immense gravitational forces trying to crush it. What happens next is nothing short of cosmic alchemy. The star collapses, imploding under its own weight. In the process, it creates a singularity, a point of infinite density where the laws of physics as we know them break down. Surrounding this singularity is the event horizon, the point of no return. Anything that crosses this invisible boundary cannot escape, not even light. This is why black holes appear black. But here's the first mind-blowing fact: black holes do not suck everything around them. If our sun were magically replaced by a black hole of the exact same mass, Earth would just continue to orbit it as usual. The gravitational pull would be exactly the same. You see, black holes don't pull like a vacuum, they bend the very fabric of reality. Einstein's theory of general relativity introduced a revolutionary idea: gravity, in a force, it's a warping of spacetime caused by mass. Think of space as a giant, invisible trampoline. Place a heavy bowling ball in the middle, and the surface bends. Now, roll a marble nearby. It won't travel in a straight line. It will curve toward the heavy object. That's gravity, not as a mystical pull, but as the natural curvature of space-time itself. Black holes take this concept to the absolute extreme. Their mass is concentrated into a tiny, tiny volume, creating a gravitational well so deep that space and time are stretched beyond imagination. This is why light cannot escape, and why nothing that crosses the event horizon ever returns. Time itself slows down near a black hole. If you were watching someone fall in, they would appear to freeze at the edge, while for the person falling, time would seem to pass normally. This warping is real, it's measurable, and it's one of the most profound mysteries of the universe. Hollywood loves to portray black holes as monstrous beasts, sucking everything around them like a cosmic vacuum cleaner. We see spaceships screaming helplessly toward oblivion, and entire planets swallowed in seconds. The reality, however, is much subtler and way more fascinating. A black hole only pulls strongly when objects get very close. In fact, if you were far away from one, you'd feel almost no difference in gravity compared to being near a normal star of the same mass. Black holes don't reach out across the cosmos to devour everything. Instead, their danger lies in that extreme warping of spacetime, the incredible tidal forces near the event horizon, and the massive energy released in their immediate surroundings. Speaking of that danger, let's talk about one of the most terrifying concepts in all of science: spaghettification. If an object or a person were to approach a black hole feet first, the gravitational pull at their feet would be much stronger than at their head. This difference in force would stretch the body lengthwise while compressing it sideways, transforming it into a long, thin, spaghetti-like strand of atoms. This isn't science fiction, it's a real consequence of tidal forces in extreme gravity. Spaghettification highlights a key truth: black holes aren't indiscriminate cosmic predators. The danger is all about proximity. Once you cross that event horizon, reality itself breaks down. Despite their danger, black holes are incredible natural laboratories for extreme physics. Around them, matter accelerates to near light speeds, temperatures soar 2 millions of degrees, and radiation erupts in powerful jets that can stretch for thousands of light years. By observing black holes, Scientists can test Einstein's theories, explore how matter behaves under unimaginable pressures, and study energy in its most extreme forms. One famous example is the supermassive black hole at the center of our own Milky Way galaxy, Sagittarius asterisk. It has a mass 4 million times that of our Sun, yet its direct influence is confined to a region no larger than our solar system. The stars orbiting it provide a live demonstration of gravitational physics in action. The extreme warping of space-time around black holes also introduces some truly mind-bending possibilities, like time travel. Near the event horizon, time slows down dramatically relative to observers far away. A few hours spent near the edge of a black hole could equal years or even decades for someone back on Earth. While practical time travel remains firmly in the realm of theory, black holes prove that the universe allows for time to behave in very strange ways depending on gravity. This isn't just a fun curiosity. Understanding these effects helps scientists explore fundamental questions about the nature of time, the origin of galaxies, and even the ultimate fate of the cosmos. But the story gets even stranger. In 1974, the legendary Stephen Hawking made a revolutionary prediction: black holes aren't entirely black. He theorized that they emit tiny amounts of radiation, now known as Hawking radiation. Over astronomical timescales, trillions upon trillions of years, this slow leak of energy could cause black holes to completely evaporate. This discovery shattered the idea of black holes as eternal cosmic monsters. Instead, it showed them as dynamic, evolving objects that are, in a sense, alive with quantum processes. Hawking radiation beautifully links the largest objects in the universe, black holes, to the smallest, bridging the gap between general relativity and quantum mechanics. Black holes are terrifying, but they are also beautiful. They create some of the most spectacular phenomena in the cosmos. Accretion disks, the swirling matter falling into a black hole, glow brightly in X-rays. Relativistic jets shoot particles across entire galaxies. And gravitational lensing bends the light of distant stars into stunning arcs and rings. The first ever image of a black hole, captured by the Event Horizon Telescope in 2019, revealed a glowing ring of light surrounding the dark silhouette of the singularity. It was a direct glimpse into the warping of space-time itself, a triumph of science, and a powerful reminder of the universe's sheer grandeur. So, you might be thinking, this is all fascinating, but what does it have to do with me? After all, the nearest known black hole is over 1,000 light-years away. But studying black holes fundamentally impacts our understanding of the cosmos and our place in it. They shape entire galaxies, trigger the formation of new stars, and control the large-scale structure of the universe. They push the limits of physics, forcing scientists to reconcile the laws of the big with the laws of the small, and they inspire our human imagination, driving us to explore, to understand, and to dream beyond our own small world. In a way, black holes teach us a profound lesson. Appearances can be deceiving. They aren't monsters lurking in the dark, indiscriminately devouring planets. They are a natural, inevitable consequence of gravity, mass, and the very structure of space-time. Understanding them requires curiosity, patience, and a willingness to see the universe not as a stage for human drama, but as a vast, beautiful, and often hostile place governed by impartial physical laws. They remind us of our fragility, but also of our courage and our relentless drive to explore. Even in the face of cosmic oblivion, humanity reaches for knowledge, observes the stars, and learns the language of the universe. So, in the end, black holes don't suck. They bend space and time. They warp reality, and they challenge the very limits of human understanding. They are both terrifying and awe-inspiring, deadly and beautiful, invisible and yet incredibly revealing. By studying them, we do more than just explore the universe. We explore the boundaries of reality, the nature of time, and the possibilities of existence in the most extreme environments imaginable. Black holes aren't just cosmic objects, they are mirrors, reflecting our own curiosity, our courage, and our eternal desire to understand the universe we call home. So next time someone tells you that black holes suck, remember, they don't. They warp reality itself. And in that warping lies the greatest story the cosmos has ever told. Thanks for watching. If you found this journey into the cosmos as fascinating as I did, make sure to like this video and subscribe for more deep dives into the mysteries of our universe. See you next time.